In continuation to the piecewise method, I am going to derive the force displacement relation for two spring systems. The springs are connected in series with three nodes. So node 1, 2 and 3. Node 1, 2 and 3. Here we can take element number 1 and element number 2. The stiffness coefficient K1 and K2 for each element. So the force here is compression, that is F1. The displacement is U1. The corresponding force is F1. Here U2, F2. At node 3 it is U3, F3. So the direction considered X from left. So we are going to assemble the force displacement relationship for element 1. So consider element 1. So it is compression. The force at node 1 is compression. So minus F1 suffix 1. It implies for the element number 1 we consider node number 1. So the upper 1 indicates the node number. The subscript indicates the element number. So while you are putting negative to the force sign, so I am making here F1 as positive and putting negative to the stiffness coefficient K1. We already learned about the displacement. The net displacement is U2 minus U1. U2 minus U1. So I am arranging in terms of U1 and U2 as the order. So it is K1 U1 minus minus K1 U2. Because the stiffness coefficient is K1. I am considering the element number 1 only. So next one, F suffix 2 superscript of 1, that is for the node 2 for the element 1. The force at node 2 for the element number 1. So it is K1. So this force is transferred from here to here. So it is also considered at node 2, it is also considered as tensile force. So K1 U2 minus U1. So that is the force is compression at node 1. While it is leaving, it is a tensile force. So to the element number 1, the approaching load is compression and leaving force is tension. That's why I am putting K1 positive. So it is K1 U2 minus U1. So I am rearranging in terms of U1 and U2 plus K1 U2. So in matrix format, for the first node for the element number 1, for the second node for the element number 1 is equal to, so this is the vector, force vector, which is equal to the K matrix into the displacement vector, that is U1 and U2. So from the first equation, K1 is the coefficient of U1 and minus K1 is the coefficient of U2. From the second equation, minus K1 is the coefficient of U1 and plus K1 is the coefficient of U2. So we have arranged in matrix format. Similarly, for the element number 2, so you can separately consider the element number 2 where the first node is 2, second node is 3, the stiffness coefficient is K2, and the force matrix is F2 at node 2 and F2 at node 3. So first F2 at node 2 is minus K2 U3 minus U2. So if you arrange in terms of U2 and U3, K2 U2 minus K2 U3. Similarly, for the element number 2 at node 3, it is plus K2 U3 minus U2. So minus K2 U2 plus K2 U3. So similar matrix format K22 and K23. So the force vector which is multiplied by stiffness and the displacement vector. Here the displacements are U2 and U3. For the first element the displacements are U1 and U2. For the second element the displacements are U2 and U3. So arrange the coefficients of these displacements. First one is K2. Here minus K2. Here minus K2 and plus K2. Okay. Now we are going to arrange the global stiffness matrix. We are forming the stiffness matrices for the element 1 and 2. We are going to superimpose all the matrices of forces, displacement and stiffness to the global formulation. How we can form the global formulation? Consider the force equilibrium. Consider the force equilibrium. Force equilibrium at node 1. That is capital F1. So initially we represent U1 and capital F1 as the force coordinate. Capital F1 is equal to force vector of first element to the first node. Capital F2, that is at node 2. At node 2, capital F2 is equal to the summation of force vector of 2 of 1. You can take 2 of 2 plus 1 of 2, the first element, the force vector of first element to the node 2 and the force vector of second element to the node 2. So we have to sum up. At node 3, F3 is equal to the second node, second element, third node, the force vector of second element to the third node. So I am going to arrange capital F1 simply the force vector of first element, that is minus K1 U2 minus U1. This is simply the first element force displacement relationship. So I am arranging in terms of U1 and U2, K1 U1 minus K1 U2. The second F2 is combination of the first element of second node and the second element of second node. So we have to combine both the equations. The first equation is K1 U2 minus U1. So that represent the first element second node force vector plus so we have formulated minus K2 U3 minus U2. for the second element. Minus is because of, so it is the spring. Here at first node we have formulated the first element, first node force vector. At node 2, here we should consider the first element force matrix at node 2. Here we should consider the second element force matrix at node 2. So this force matrix is minus K2 U3 minus U2, because for the first node it is compression force, at the second node of first element it is tensile force. At the same time, for the second element at node 2 it is a compression force, at node 3 it is a tensile force. Tensile force for the corresponding node 2 it is compression force. For the corresponding element 1 it is a tensile force. For the corresponding element 1 it is a compression force. So F22 is minus K2 U3 minus U2. So I am going to arrange in terms of U1, U2, U3. So minus K1 U1 plus K1 U2 plus K2 U2 minus K2 U3. So minus K1 U1 plus summation of K1 plus K2 for U2 minus K2 U3. So this is F2. Similarly, F3 is simply the force vector of last element. So here the last element subjected to tensile force, it is a positive quantity, that is K2 U3 minus U2. So we are arranging as the order of U2 and U3. So minus K2 U2 plus K2 U3. So now we are going to form the global stiffness matrix. So we have to consider the order U1, U2, U3 and the force vector F1, F2, F3. F1 and F3 does not change, but F2 is summation of the force vector from the first element to the second element. So we have to consider these three equations 1, 2 and 3 to arrange the matrix format. So the first, the coefficient of U1 and U2 are K1 and minus K1. So you put K1 minus K1. The third, there is no effect on U3. The force vector does not have effect on the displacement at third node. So simply you put 0. For the second equation, all the three components are available, U1, U2, U3. The coefficient of U1 is minus K1. The coefficient of U2 is K1 plus K2. The coefficient of U3 is minus K2. For the third node, for the second element, consider the equation 3. There is no U1. U1 is 0. U2 is minus K2. U3 is plus K2. So now we have completed the element, stiffness matrix. So we can easily divide the above equation as K1 minus K1 0 minus K1 K1 0. All other elements are 0 at node for the element 1. Here it is U1, U2, U3. I am separating the above matrix, that is here F1 of 1, F2 of 1 and 0. The third force vector is 0. The next one on the equation is 0, 0, 0, 0, 0. The middle component is K2 minus K2. here minus K2 and K2, which is U1, U2 and U3, which is 0, F2 of 2 and F3 of 2. So this is the force vector. So in this way we can assemble the global stiffness matrix for the spring elements which is connected in series. Also can be formulated for the spring elements connected in parallel. We will see one numerical example to calculate the forces displacement in a spring system.